When you open Google, send a WhatsApp message, or watch a YouTube video, have you ever wondered how your data knows exactly where to go? Think about that for a second. Right now, billions of people around the world are sending messages, streaming videos, making video calls, and loading web pages, all at the same time. And somehow, your message reaches your friend and not a stranger. Your Netflix show loads on your screen and not your neighbor's. Your Google search returns results in less than a second from a server that might be thousands of miles away. That doesn't happen by magic. It happens because of invisible rules, a hidden architecture that sits underneath everything you do online, and almost nobody knows it exists. Today, you're going to be one of the few people who does. Here's why this matters more than you might think. Every cybersecurity professional, every network engineer, every ethical hacker, and every IT administrator builds their knowledge on one foundation. Before you can understand firewalls, before you can understand how hackers intercept data, before you can understand virtual private networks, network attacks, or even how the internet itself actually works, you need to understand the OSI model. Without exaggeration, it is one of the most important concepts in networking, and yet most beginners skip it, rush through it, or memorize the 7 layers without ever truly understanding what they mean. That's exactly why this video exists. Now, back in the 1970s, the internet as we know it today didn't exist yet, but different companies were already building their own networks, and there was one major problem. A network built by one company couldn't communicate properly with a network built by another. Each one used different rules, different formats, different languages. It was chaos. Imagine if every smartphone manufacturer used a completely different system for phone calls, and your phone simply couldn't connect to someone using another brand. That was the reality of early networking. So in 1984, the International Organization for Standardization, commonly known as ISO, published a framework called the Open Systems Interconnection Model, or simply the OSI model. Its purpose was simple: to give the world a common language for network communication, a universal rulebook divided into 7 distinct layers, with each layer responsible for a specific job. And by the end of this video, you're going to understand every single one of them. So what exactly is the OSI model, and why does it even exist? Let's think about the postal system for a moment. When you want to send a letter to someone across the country, you don't just throw it out the window and hope for the best. There's an entire system working behind the scenes. You write your message, you fold the letter, place it inside an envelope, you write the destination address, you add a stamp, and then you drop it at the post office. From there, a network of workers, vehicles, sorting centers, and delivery routes make sure that letter reaches exactly the right destination. Every step has a specific job. Every step follows a specific order. And because postal systems around the world follow similar standards, a letter sent from Tokyo can arrive in Toronto without anyone having to invent a completely new process. The OSI model works in exactly the same way, but instead of moving letters, it moves data. OSI stands for Open Systems Interconnection. It was created during the late 1970s by an international standards organization called ISO. At that time, the world was rapidly realizing that computers needed to communicate with one another. The problem was that nobody could agree on how that communication should happen. Different companies were creating networks that worked only with their own hardware and software. Once again, it was chaos. So the OSI model was designed as a universal blueprint, a common language that any network, any device, and any software system could follow. It breaks the entire process of network communication into 7 separate layers. Each layer has its own responsibility. Each layer performs a specific task, and together those layers make modern communication possible. Think of them as 7 departments within a giant postal service. Each department does one job, passes the information to the next department, and works together to make sure your data travels from one device to another reliably, accurately, and in a way that every device on Earth can understand. So here we are. Your fingers have just typed www.google.com into your browser, and you hit enter. In that single moment, something remarkable begins. Your data is about to take a journey through 7 distinct layers, and each one has a very specific job to do. Let's start at the top, the place where you actually interact with the network. Layer 7, the application layer. The application layer is the only layer you ever truly see or touch. It's where humans meet the network. When you open Chrome or Firefox, when you send an email, when you scroll through Instagram, or send a WhatsApp message, you are interacting with the application layer. But here's something that confuses a lot of beginners. Your web browser is not the application layer. Your browser uses the application layer. The layer itself is really about the rules and communication methods that allow software to talk across a network. So when you type google.com and press enter, your browser immediately knows it needs to make a request. To do that, it uses a protocol called HTTP, or more commonly today, HTTPS. Think of a protocol as a language. HTTPS is simply the language that both your browser and Google's servers understand. Your browser is essentially saying, "Hello Google, could you please send me your homepage?" That request, that question, is the data that now needs to travel across the internet. But before it can begin its journey, it needs to be prepared. And that's where we move down to layer 6, the presentation layer. If the application layer is about what you're asking for, the presentation layer is about how that information is prepared. Think of it as a translator and a security officer working side by side. Its job is to make sure the data is formatted correctly so both devices can understand it. Imagine two people speaking different languages. A translator makes sure both sides understand the same message. That's one of the presentation layer's responsibilities. It also handles compression. Think of compression like carefully packing a case. The same belongings fit inside, but they take up less space. Smaller data means faster transmission across the network. But perhaps the most important responsibility of the presentation layer today is encryption. When you see that small padlock icon in your browser's address bar, that's security working behind the scenes. The presentation layer uses a technology called TLS, which stands for Transport Layer Security. TLS scrambles your information into unreadable text. So if someone intercepts the data while it's traveling across the internet, all they see is meaningless gibberish. Your request is sealed like a confidential letter inside a locked envelope. Only the intended recipient has the key to open it. At this point, your data is formatted, compressed, and encrypted. But there's still an important question. How do your computer and Google server know they're having a conversation with each other? And how does your request avoid getting mixed up with millions of other requests moving across the internet at the exact same time? That's the responsibility of layer 5, the session layer. The session layer manages communication sessions between devices. A session is simply an ongoing conversation. When your browser connects to Google, the session layer establishes that conversation. It's similar to two people starting a phone call. One person says, "Can you hear me?" The other replies, "Yes, I can." And now the conversation can begin. Throughout the communication process, the session layer keeps track of the exchange. It knows which messages belong to which conversation. And when the communication is complete, it closes the session properly. No confusion, no loose ends. By this point, your data is already taking shape. It knows what it wants. It has been formatted, protected, and assigned to an active conversation. Now it needs to be packaged, addressed, and physically delivered. And that's where the lower layers take over. So we've handed our data to the session layer, the conversation has been established, everything is organized. But now we face one of the biggest challenges in networking. How do we make sure the data actually arrives? All of it, in the correct order, without anything getting lost along the way. That's the responsibility of layer 4, the transport layer. Imagine ordering a large piece of furniture online. It's too big to fit into a single box. So the company splits it into several packages. Box 1, Box 2, Box 3. Each package is labeled and shipped separately. They might even travel along different routes, but when they arrive, you know exactly how they fit together. And if one package never arrives, you can request a replacement. That's exactly what the transport layer does with data. When your request reaches layer 4, it gets divided into smaller pieces called segments. Each segment receives a sequence number. That way, the receiving device knows exactly how to put everything back together. The transport layer also uses something called ports. Think of a port as a specific door on a building. Different services use different doors. Secure websites commonly use port 443. Email services use different ports. Online games often use others. Ports help a computer understand exactly which application should receive the incoming data. Now the transport layer must make an important decision. Should the delivery prioritize reliability or speed? For web browsing, reliability is critical. So the transport layer uses a protocol called TCP, Transmission Control Protocol. TCP carefully checks that every segment arrives successfully. If anything goes missing, it sends it again. But some applications value speed more than perfection. Video calls, live streaming, online gaming. In those situations, waiting for every missing piece can cause noticeable delays. So they often use UDP, User Datagram Protocol. UDP sends the data immediately and doesn't wait for confirmation. Speed over perfection. Since we're loading a website, our request uses TCP. The segments are numbered, assigned to port 443, and passed down to layer 3, the network layer. This is where the internet truly comes alive. The network layer answers one enormous question. How do we send data from your device to a server that could be located on the other side of the planet? The answer is simple: IP addresses. Every device connected to the internet has an internet protocol address. Think of it like a home address in the real world. Your computer has one. Google's servers have one. The network layer takes the segments and packages them into packets. Then it labels those packets with both the source and destination IP addresses. In other words, where the data came from and where it needs to go. But knowing the destination isn't enough. You also need a route. That's where routers come in. Routers are the traffic directors of the internet. Whenever a packet reaches a router, the router examines the destination address and decides where the packet should go next. This process happens again and again and again, hop after hop, router after router, across cities, countries, and continents, until the packet eventually reaches Google's network. The network layer makes worldwide communication possible. Next comes layer 2, the data link layer. While layer 3 manages the global journey, layer 2 focuses on the local journey, the short trip between your device and the next device on the network, usually your router or a network switch. Instead of using IP addresses, layer 2 uses MAC addresses, a media access control address. Every network card has one. Think of it as a permanent hardware identity. The data link layer wraps the packet inside something called a frame. It then labels that frame with the MAC address of the very next device it must reach. Not the final destination, just the next step. And finally, we arrive at layer 1, the physical layer, the lowest layer of the entire model. This is where data leaves the digital world and enters the physical world. The frames are converted into signals, electrical pulses moving through copper cables, pulses of light traveling through fiber optic lines, or radio waves moving through the air when you're connected through Wi-Fi. At this layer, your carefully prepared data becomes pure physical energy, traveling across real-world infrastructure toward its destination. 7 layers, 1 journey, and we're only halfway through the story. So now you've met all 7 layers, but this is the moment where everything finally comes together. In fact, this is the part that makes the entire OSI model click into place. It's called encapsulation. And once you truly understand encapsulation, the whole model suddenly starts making perfect sense. Let's go back to our postal service example. Imagine you're sending a letter. First, you write your message. Then you place it inside an envelope. You write the destination address on the outside. Maybe you add a tracking label, and then you hand it over to the postal service. Notice what happened. At every step, new information was added around the original message. The message itself never changed. It simply became wrapped inside additional layers of information. That is exactly what encapsulation is. When you type www.google.com and press enter, your data begins its journey at layer 7, the application layer. At this point, it's simply an HTTP request. Think of it as a note that says, "Hello Google, please send me your homepage." Right now, it's just raw data, nothing more. Next, the data moves down to layer 6, the presentation layer. Here, the information is prepared for travel. The data is formatted, and more importantly, it is encrypted. The request is transformed into a secure format that can safely travel across the internet. It's still the same data, but now it's protected. Then the request reaches layer 5, the session layer. This layer adds information that identifies the conversation taking place. Think of it as attaching a label that says, "This message belongs to this specific communication session." That way, the devices on both ends know exactly which conversation this data belongs to. Then we arrive at layer 4, the transport layer. And this is where something very important happens. The data is divided into smaller pieces called segments. Instead of sending one large block of information, the transport layer breaks it into manageable chunks. If TCP is being used, each segment receives sequence numbers. Those numbers allow the receiving device to rebuild everything in the correct order later. The transport layer also adds source and destination port numbers. These ports act like specific doors that applications use to send and receive information. Now our segments move down to layer 3, the network layer. Here, each segment is wrapped inside a packet, and that packet receives something extremely important: IP addresses. One address identifies where the packet came from. The other identifies where it needs to go, just like writing a sender and recipient address on a package. Now the packet knows exactly where it belongs in the world. Next comes layer 2, the data link layer. The packet is wrapped once again, this time in something called a frame. The frame receives MAC addresses. These addresses help devices communicate on the local network. Think of them as directions for the next immediate step of the journey, not the final destination, just the next stop. And finally, the data reaches layer 1, the physical layer. Everything is converted into raw bits, ones and zeros. Those bits are transformed into electrical signals, light pulses or radio waves, depending on how the network connection is being used. And just like that, the information leaves your device and begins traveling toward its destination. Now, let's reverse the process, because eventually those signals arrive at Google's servers, and when they do, the entire journey happens in the opposite direction. This reverse process is called de-encapsulation. The physical layer receives the signals and converts them back into bits. The data link layer removes the frame information, the network layer removes the packet information, the transport layer removes the segment information. The session layer processes the session details. The presentation layer decrypts and formats the data. And finally, the application layer receives the original request, exactly as it was created on your computer. Layer by layer, the extra information is removed until only the original message remains. That's de-encapsulation. So here's the simplest way to remember it. As data travels down the OSI model, each layer wraps it with additional information. As data travels back up the OSI model, each layer removes that information. Going down, data gets wrapped. Coming up, data gets unwrapped. That's encapsulation and de-encapsulation, and together they are the reason devices can communicate reliably across the internet. Now let's bring everything together with a real-world example. The exact example we've been building toward throughout this entire video. You're sitting at your computer, you open your browser, you type www.google.com, and you press enter. Simple. You've probably done it thousands of times. But what actually happens during those few moments? Let's walk through it one layer at a time. The instant you press enter, your browser recognizes that you want to load a web page. This is layer 7, the application layer. Your browser creates an HTTPS request, a message that essentially says, "Hello Google, I'd like to view your website." That request is then passed down to the lower layers. At layer 6, the presentation layer prepares the data for transmission. The information is formatted correctly. And because modern websites use HTTPS, the request is encrypted. That small padlock icon you see in your browser, this is one of the reasons it exists. Your request is protected before it ever leaves your device. Next comes layer 5, the session layer. A communication session is established between your computer and Google's server. Think of it as opening a conversation channel. The session remains active while information is exchanged between both devices. Then the request moves to layer 4, the transport layer. The request is divided into segments. TCP takes responsibility for reliable delivery. Each segment receives sequence numbers so everything can be rebuilt correctly later. The request is also assigned port 443, the standard port used for secure web traffic. Now the data moves to layer 3, the network layer. Each segment becomes a packet. The packet receives 2 addresses, your IP address and Google's IP address. With those addresses attached, routers across the internet know exactly where the packet needs to travel, hop by hop, router by router. The packet moves closer to Google's servers. At layer 2, the data link layer wraps each packet inside a frame. MAC addresses are added. These addresses help devices communicate on local network segments as the journey continues. Finally, the data reaches layer 1, the physical layer. Everything becomes electrical signals, light pulses or radio waves, and those signals are transmitted across the physical network infrastructure of the internet. Eventually, Google's servers receive the signals. And then everything happens in reverse. Each layer removes the information added by its counterpart. The request travels back up through all 7 layers until Google's application layer finally receives and understands the message. Google processes the request, builds a response, and sends the web page back through the exact same 7-layer journey. All of this happens in a fraction of a second. So the next time you open a website, send a message, or watch a video online, remember this. Behind that simple click is a remarkable process involving 7 layers, countless devices, and an extraordinary amount of coordination. And that process is the OSI model working in real time. Now here's where things get really interesting. And honestly, this is the part most basic networking courses completely skip. The OSI model is not just an academic concept. It is the foundation of everything cybersecurity professionals do every single day. Think about it like this. If you are trying to defend a building, you need to know every entrance, every corridor, every floor. The OSI model gives cybersecurity professionals exactly that kind of blueprint for a network. Every layer is a potential entry point, and every layer is something an attacker can target or a defender can protect. Let's start with firewalls. When you hear the word firewall, you might imagine one giant wall blocking bad traffic, but modern firewalls are far more advanced than that. They actually operate across multiple OSI layers. A basic firewall works at layer 3, the network layer, filtering traffic based on IP addresses, deciding which packets are allowed in and which are dropped. A more advanced firewall, called a stateful firewall, also works at layer 4, the transport layer, checking ports and connection behavior to determine whether a connection is actually legitimate. And the most advanced systems, called next-generation firewalls, go all the way up to layer 7, the application layer, where they inspect the actual content of your traffic to detect hidden threats inside normal-looking requests. Now let's talk about packet sniffing. And yes, it sounds exactly like what it is. It means capturing and analyzing data packets traveling across a network. Tools like Wireshark allow security analysts to see raw network traffic starting from layer 2 and layer 3, and then peeling back each layer to understand exactly what is being transmitted. Security professionals use this to troubleshoot networks and detect unusual activity. But attackers can also misuse it to steal sensitive information if that data is not properly encrypted. And that brings us directly to VPNs. A VPN protects you by encrypting your data at higher layers before it ever leaves your device. So even if someone captures your packets, all they see is unreadable noise, just random data, completely useless. Now let's talk about DDoS attacks, distributed denial of service. These are basically massive floods of traffic designed to overwhelm a system. Some attacks target layer 3, flooding networks with useless packets. Others target layer 4 by exhausting connection resources. And the most dangerous ones target layer 7 because they mimic real users and overload the actual application itself, making it crash from the inside. This is why every cybersecurity professional learns the OSI model first, because you cannot defend what you do not understand. Now, before we wrap up, let's talk about the mistakes that confuse almost every beginner, and avoiding these will save you a lot of frustration later. The first mistake is memorizing the layers without understanding them. Yes, you can use mnemonics like, all people seem to need data processing, or please do not throw sausage pizza away. Those are fine for exams, but useless if you don't understand what is actually happening. If you can say all 7 layers perfectly but cannot explain them, you haven't really learned them all. You've only memorized words. The second mistake is confusing the OSI model with the TCPIP model. These are not the same thing. The OSI model is a conceptual framework, a way to understand and visualize how networks work. The TCPIP model is what the internet actually uses in practice. Think of it like this. OSI is the blueprint. TCPIP is the real building. Both are important, but OSI makes everything easier to understand. The third mistake is skipping encapsulation. Many beginners learn the layers like a simple list, but never understand how data actually moves through them. Encapsulation is the process that makes everything work. Without it, the model is just theory. Now, take a moment and look at how far you've come. You now understand why the OSI model exists. You understand what happens at each of the 7 layers. You understand how data travels across the internet, getting wrapped and unwrapped at every step. And you understand how real-world tools like firewalls, VPNs, and packet analyzers connect directly to this model. Most networking students spend weeks struggling with this topic. You just understood the foundation in one video. But more importantly, you didn't just memorize it, you actually followed the story. And that changes everything. Because the OSI model is not just another topic, it is the foundation of networking. Every protocol, every attack, every defense, Every system you will ever learn in cybersecurity builds on exactly what you learned today. You now understand the language of the internet. And once you understand that, you're no longer just a user. You're someone who understands what's happening behind the screen. And that is a completely different level. The fact that you stayed till the end says everything. If this helped you understand something that once felt impossible, then you're exactly the kind of person who should go deeper. Share it, comment your thoughts, and subscribe, because this is just the beginning.